Welcome to our last lecture in Bio 24, talking about life on other planets. When looking for life on other planets, most often we look for carbon-based life. What is it about carbon that makes it so important to living systems? Well, carbon itself is a fairly small atom. The reason why this is important is that atoms are made in stars, like our sun. And it turns out that smaller atoms are much easier for the stars to make than larger atoms. Because it's easier to make small atoms, there are more of them. So when looking for elements that would be found in living systems, which are highly complex and would require many molecules, a small element or atom is important because we'll need a lot of that element in order to form life. In addition to being small and plentiful, carbon is also important and thought to be a key factor for life because it can bind to 4 other atoms at once. In doing so, it can generate very complex molecules, like you see here. These complex molecules can be found in living systems like DNA structures, proteins, and so forth. If the atom could only bind to 1 or 2 other atoms at once, then there would not be enough complexity in the molecules to generate a structure as complex as life. Usually, carbon incorporates hydrogen atoms as well. This forms what are known as hydrocarbons. And carbons can form structures including oxygen and nitrogen, and in so doing can form double or triple bonds too, increasing the complexity even more. Another alternative for carbon that you may have heard of is silicon. Silicon is larger, which means there is less of it in our solar system and universe, but it can also bind to many atoms at once and form complex molecules, making it an obvious possibility for the basis of life elsewhere. Water is also extremely important to living systems. Without water, life would not exist. What's so special about water molecules? Well, water molecules form when you just have 1 oxygen atom bound to 2 other hydrogen atoms. This makes a molecule that ends up being polar and can interact with lots of other atoms and molecules itself. This makes water a universal or very good solvent because lots of other molecules can interact with it and dissolve in its liquid. That includes sugars, salts, DNA molecules, and some proteins. Water also has a high heat capacity. Now, water itself also has a high heat capacity. Heat capacity is the amount of energy that's needed in order to raise the temperature of that solution by 1 degree Celsius. Compared to other molecules, the amount of energy needed to raise the temperature of water is really high. This is because water can interact with itself and form hydrogen bonds like you see here. These hydrogen bonds keep the water molecules attached to each other. And when energy is added, that energy is not added to increase the movement or vibration of each individual water molecule, but instead the energy is used to sever or break the hydrogen bonds. So in order to increase the temperature of water, it takes a lot more energy because of the hydrogen bonds keeping those molecules attached to each other. Water also has a high heat of vaporization for much the same reason. The high heat of vaporization means a lot of energy is needed in order to break these hydrogen bonds and turn liquid water into vapor water or steam. These features play a really important role in living systems. Water having a high heat capacity because of the hydrogen bonds means that any organism that's comprised primarily of water will not change its temperature readily. For living systems, it's really important that our water molecules and the rest of the molecules in our systems don't change temperature easily. If we were to change temperature rapidly, that could result in death. In addition, the high heat of vaporization means that it's easy for us to cool ourselves down. We use sweat in order to do this. So when we sweat, in order to turn that liquid water into vaporized water or steam and evaporate off of our bodies, it draws a lot of energy into the sweat in order to cool us off. You can feel the same thing if you put water onto your skin. You can feel the energy being stripped out of your body at that area. On the other hand, if you use an oil, oils don't have high heat of vaporization and they don't have this property. So you don't feel cooler when you cover your body in oil. Finally, water molecules are cohesive and adhesive, which means that they stick to each other and also stick to other molecules easily. Again, a result of these hydrogen bonds. Water has a high surface tension, again because of the hydrogen bonds. Because the hydrogen bonds are keeping the water molecules together, liquid water has a high surface tension. You can actually see this in organisms like water striders, insects that can walk on the surface of water, or even skipping rocks on a lake. Finally, frozen water is less dense than liquid water, which is an interesting property. When water freezes, the molecules are actually farther apart than when water is in the liquid state. Because water is less dense than liquid water, this means that ice floats. And as a result, in really cold areas, the ice forms on the top first, protecting the living systems underneath in the lake from the colder temperatures in the air. Now, why do we think there's life on other planets? Well, we've already discovered that there's over 1,000 planets that we've been able to observe and determine their location. Dozens of these have the potential for life. That's because we've found the possibility for carbon all over our universe and water all over our universe. Many of these planets were discovered using the Kepler Space Telescope. In fact, the Kepler telescope was designed and manufactured for this express purpose, to identify planets in our solar system and galaxy. Given the size of our galaxy and of our universe, it's very unlikely life would not exist anywhere else. This is what's referred to as the Copernican principle, that Earth is not the only possible source of life in our universe, and that our universe is so expansive and so big that it's very possible life could have evolved elsewhere. These planets, discovered in other solar systems in our galaxy, would have to reside within what's called the habitable zone in order to support life. The habitable zone is an area within a solar system that would include a space that's not too hot or too close to a star in order to result in all of the water becoming vapor, and also not being too cold or far away from the star where all of the water would end up being solid and frozen. Earth just happens to be in the middle of this habitable zone where we can have liquid, solid, and gaseous water. Using interferometry, which combines the light wave images from satellites, we can determine what kind of elements are found in other planets elsewhere, in other solar systems. And from this, we can determine what elements or molecules exist on a given planet. So we can identify which of the thousands of planets that have been discovered contain a lot of carbon, hydrogen, and oxygen for the possibility of life. Given that, we can say that we've found some areas where there are possibilities for life elsewhere. But most of the investigations today are focused on finding places in our solar system where life could reside, because Earth might not be the only place. The first main target, of course, is Mars. One of the primary reasons why Mars is currently a hot investigated topic in the possibility for life elsewhere is that there is a lot of evidence now that liquid water is found on the surface of Mars, specifically at the equator where it's warmer, and it's only found there seasonally, essentially in what would be equivalent to Martian summer. But during those times, there is evidence that frozen water can thaw and melt and form liquid water before it evaporates as a result of a lack of atmosphere. In fact, there's evidence that there used to be so much liquid water on Mars that canals or canyons were formed from rushing water. There's also evidence that there was liquid water on Mars in the form of gypsum. Gypsum is a hydrated molecule, and the only way that it can form is if the molecule makes contact with water. Mars, of course, very likely may still have liquid water beneath the surface where life would most likely exist without an atmosphere. So investigations still remain underway into this possibility. Those investigations use Martian rovers today. Curiosity was one of the more recent Martian rovers used for this purpose. It was launched in fall 2001 and remained roaming the planet for years, far longer than it was initially intended. This Martian rover looked for lots of different minerals and gases, and in fact found some evidence for methane. Methane is an organic molecule, being CH4, and this organic molecule on Earth is primarily produced as a result of living systems. 90% of the methane on Earth is made by living systems. The other 10% is from contact between rock and flowing water. So the presence of this methane indicates that either there's living bacteria called methanogens that would be producing methane on Mars, or there's liquid water making contact with rock, resulting in the formation of methane. Methane disintegrates pretty quickly, and so in order for this Martian rover to detect methane, it would likely have to be a recent production of methane on the planet. There are currently new rovers being designed by European space agencies and NASA to look for the possibility of these methanogenic microbes on Mars in the future. In the next section, we're going to talk about the possibility of life in other areas in our solar system.